There's Matt.
To discuss this.
What?
I'll just text you.
Yeah. It's like very on task. Exactly. It's like, I don't know. Like it's the first. It has to be probably the first one. I don't know. Yeah. Kind of curious.
You make it hard, but
You were right the first time.
You go to the doctor or
no. I'm a doctor.
you don't listen. So she went and yeah, that's what she said. We walked into this event and they have this massive and I'm like
What's that?
10th year anniversary of the golf program, and that's not that. They do every fall in my school. They do this golf event where like you pay a certain amount of course when you go out. It's way more than you would ever pay.
Yeah,
It's a fundraiser. So it's a big fundraiser for financial aid. I love speaking. Talking about how golf plays broadly like athletics I can plays has had an impact on my life and why.
What sports do you play?
I played basketball and cross country for a year and then I
So, few announcements. First off, thank you for your feedback on Thursday. Very useful, as always. I'm trying to respond to many of the things that you wrote about. So, this will be one of them. So some of you at the back liked amplification. Okay. So, maybe not that much amplification. Some of you have read your email today. We'll see that I posted something about schedules. I won't say anything in class about recitation schedules the weeks of Election Day and Thanksgiving. Just please read your email and I will get back to you on that fairly quickly. The other one had to do with final exam schedule. We're only in week 4, I think, in class. Many of you are in your first season here at Columbia. You probably already know the final exam week period. Runs this year pretty late. I think the last formal day of exams is Thursday, December 20th, which turns out to be the date that our final exam is scheduled on. So please, since taking the final exam is obviously a requirement for passing the course, please make sure you don't schedule any holiday, winter break travel. such that you will miss the final exam, okay? So it's on that Thursday morning, according to the tentative schedule put out by the registrar. I was also the recipient of an email from the registrar yesterday asking to schedule review sessions for the final exam, of which there will be at least 2. Usually I try and do that during reading week for obvious reasons. So reading week is only probably 3 days or something like that. But I'd just like you all before Thursday, because I'm going to try and figure out when to schedule them, because I have to tell the registrar next week. Just take a look at your own schedules for those reading days, presuming they're free, but also final exam days, just so that I can call you on Thursday and try and figure out when the optimal time to hold those review sessions is. Okay, so long way off. I don't want to say any more about the final exam. We're only just really getting started. Okay, clearly I had not appreciated the lack of use of the answers provided in Mastering Physics. So what you really need is real solutions. I will be endeavoring to get those up as soon as possible. And also providing a better set of practice problems for you. So keep your eyes peeled for that this week. I hadn't realized quite how illuminating the answers are in Mastering Physics. So you do need real solutions. Okay. The person who left their drinking cup in my office hour last week, I have it. But you can't pick it up until after class because I'm going to use it. Okay. Not to drink out. All right. Was there anything else? Yes, working problems in class. So we're going to do that right away. All right. So just about the homework this week. Again, some of it's fairly challenging, and you will be doing practice problems in recitations today and tomorrow, but I thought since you requested it, very correctly so, we start off with a Newton's Law problem the first thing in class. I'm inclined to ask you to work it with your neighbors for a few minutes, and I think I will, but I don't want this to go on too long, because I do want to talk about a couple of additional forces, or in one case an additional force, in the second case with circular motion, not an additional force, but looking at the dynamics of circular motion. So let me, with that said, set up a initial problem to work on. Let me get rid of that. Okay. All right, so here it is. I'm going to set up the following example. This is from Mastering Physics, but I unfortunately didn't have a chance to figure out which number problem. Okay, so let me just set this up, and then I will talk you through it. Okay, so this is the sketch of the situation we're going to analyze. A little bit different perhaps than we've seen previously. Anything that has these sort of hatches is supposed to be a fixed surface. So you might imagine this being the edge of a table or a bench. This is a vertical wall. We have 2 blocks, A and B. I'll tell you something more about that in a moment. They are connected by strings, but the string itself is connected to, I guess, what I'm going to describe as another string, in such a way that that string is attached to the wall up here, and the whole thing is suspended. Okay? So it's a slightly contrived situation, but let's see what we can figure out. I'm going to give you some pieces of information. So, as much as I don't like to use weight for the gravitational force, I'm going to use the symbol WB here. So the gravitational force acting on object B is 711 newtons. There is friction on that surface, and there is a coefficient of static friction between the block and that surface, which is 0.25. The angle with which that second or additional piece of string is oriented with respect to the horizontal is 30 degrees. That's what we're given. Question is, what is the maximum weight? Again, another word I particularly like to use, but I think it was used in this problem, of block A, for which the system remains stationary. Okay, so let me just pass this a little bit more, and then I'm going to ask you to work with your neighbor for just 2 or 3 minutes on trying to figure out how you would set this up. And I will tell you right off the bat that there's a new feature to this, which we haven't really seen before. Okay, so 2 blocks connected by a string, themselves connected by another string to a wall. They both have masses, therefore they both have gravitational forces, of course. And the question is, what's the maximum mass or weight that I can give this thing such that the whole thing doesn't start moving? And of course, if it were to move, you can imagine what would happen. This is going downwards, it's dragging this thing, and then eventually the whole thing falls off. So the question is, what is the maximum weight for which the system remains stationary? Okay, so 2 things I want you to think about, and then I'm going to ask you just to work on this with your neighbor for a little while. First is, whenever you see something that is stationary and you are being asked to say something about a limiting case, maximum or minimum, maximum more typically I would imagine, what does that sort of start to, what sort of things start to swim around in your mind when you hear that? Yeah?
An inequality.
Okay, so the response was an inequality. Let's see. Acceleration is 0, so we want it to remain static. Let's go right to back. Forces cancel, in some sense I sort of say that's similar to saying it's static. Okay, same response really. Forces cancel. But what is it about the maximum weight for which this, in this case, this block, the mass that it can have?
Reaching that point where something goes from static friction to kinetic friction.
Okay, reaching that point where something goes from static to kinetic. Good. So that's, remember, static friction has this unusual behavior that it kind of responds according to a lateral force that's applied, to the extent that it can, up until it reaches some maximum. Then the thing starts slipping and we're in the domain of kinetic friction. So that's the key thing that this problem elucidates for us. It's going to ask, what is the maximum? Of course, if this thing was super light, it's not going to move. So the question is, what's the limiting case before this thing suddenly transitions from being at rest to slipping and sliding? Okay? So whenever you see something like that, and then once you've done it once, it's kind of going to sink in and be nestled in your neurons for a while. I want you to be thinking of that. Now the other thing which is interesting about this is so far we're used to drawing free body diagrams for blocks, masses, not a whole lot else in fact. This problem is going to introduce a new feature, and it's pretty much the only case where you'll see it, I think. And it has to do with the string configuration here. Because what we have in this problem is not a string that simply connects 2 objects, whether it's straight or it wraps over a pulley, but we have a string itself which connects to another string. And this is, I think, the first time we've seen this, and needs to be treated in a special way. So there's no way, I think, that you would necessarily guess, deduce, think about what that special way is, so I'm just going to tell you. It means we have to treat that string junction, or a knot, as an object. and draw a free body diagram for it. Okay? So, with that said, I'm going to let you guys get underway, find a neighbor to talk to, and just discuss how you would approach this problem. Again, I'm not particularly interested in working through to its end, but I want you to discuss how you would set it up and then kind of work through that to solve it. Okay? So I'm going to give you a few minutes to work on that. Go ahead.
It's probably going to be I'm just going to draw out figure out what the weight yeah, this is going down. Yeah. Anything in this direction. It's 30,
It's 30? Oh yeah, he did.
yeah. What is it? No, 60, 90 triangle.
Oh wait, no, but you have no way.
I forget what it is. Or is it two? Isn't it in a 30? What are the sides of the Oh, guys.
This is 2-way day and this is way 3.
Okay, this is 2-way day. And this is way day.
178.
Yeah. So then you would have to subtract the weight of A times root 3.
Well, what I did is I said 178 minus weight.
What'd you get? Oh, because we decided already that this is 178. Okay. So
No, the weight of block B. Yeah.
So this is 178 minus, but isn't it?
Wait, no, it's weight A root 3 minus 178.
Oh, yeah.
Is it?
Well, if you do it this way, then yes. Because this is the positive direction. Minus 178. That's what the x direction is. And then
Let's say weight A
equals 0.
Yeah. Plus 178.
Right? It has to equal 0. Because it's not moving. So that means that the x component has to equal plus.
Like how I think of it is like
Weight A divided by then weight A.
we have
Right?
right, it's not just like and then you have like
Are you sure?
Am I sure?
Like, I don't get like this force is out this way.
No, I'm saying the combination of the two. Because since there's no motion, because there's no,
Oh wait, this is just 178.
because there's no,
So then we'll discuss how we're going to solve this.
so it should just be 102, which makes sense, because it has to be less.
so then if you work back to that this here
I could be wrong, but this
No, I
is
think you're right.
right? So and then we
okay. I was like, what? You can only use 3 sig figs, so to do grade 103,
They want to.
102.7.
that's
So I think it's 103.
Oh, I have a pretty
sine theta. You know what?
stuff on it.
Just use the 3060 90
I did.
all the way back up.
I know, okay, like, honestly, the graphics probably, like, when I got this, it was like, I love the guy, honestly.
Well, actually, it's a small movie. Especially this, the forces,
Step it up.
So actually,
You're 89,
I
but
read
they're
the
like,
letter to we didn't use any. You might be right. I don't know. We didn't use any cosine or whatever.
Yeah, we're
I know, but yeah, I know, but
So then, like, this is the way where it's like just about.
Okay. So as always, I'm not worrying about getting to the end, but what I want you to help me out with is three kind of essential standard steps to solving a problem like this, and it's true of any Newton's law type problem. All right, so first thing I always would want you to do is draw free body diagrams, okay? So I've got to start it over on the left-hand side here. BA, and as I mentioned, we're going to need one for the knot, unusually in this situation. Okay, so hopefully you're all in the habit now of running down your mental checklists of all possible forces that can act on objects. What do I need for object B? Which forces can you identify for me? Yeah.
first the weight.
Okay. I'm going to actually, even though you know I don't like this, I'm going to note it by W for the weight. Yep.
Normal.
Okay. Normal force. I guess I'm going to put a subscript V here. What else? Yeah.
friction,
Friction. Which way?
to this way.
Okay. So, we talked quite a bit last time, and you'll see my email over the weekend about friction subtleties.
Or
But what's very
opposing.
clear in this case is that any force exerted sideways, laterally, on object B is to the right. And so friction for sure is to the left. The notation here is not particularly consistent. I'm going to put an S there, which maybe I'll come back to in a moment. What else, if anything? Yeah. Okay, and it's being applied via a string. So I'm actually going to call this the tension on B. Anything else? Okay, I don't see any hands. Good. 4 forces. What about A? Yep.
Tension on A in the upper region, the force of gravity on A.
Okay, very good. Pull out WA. I don't see anything else there. We good? All right, the knot is interesting. As I said, usually, but we do need to draw a free body diagram for this. What forces are exerted on this knot? And I will tell you just up front that all our strings are assumed to be massless, which is going to be pretty much the case throughout. Okay, so forces acting on the knot. Let's see, who hasn't yet answered in the blue t-shirt? Yes.
Oh, yeah. The tension of A downwards.
Okay. I like that. Anything else? Yep.
X component of the tension upwards.
Next component of the tension upwards. What do you mean?
The force of tension is just like the tension of like on the knot.
So just remember, and maybe you'll say something which is fine, actually, it's maybe not interpreting it correctly. All we want to do is identify the forces that act on this knot.
Yeah, so the tension force that's like acting on the knot.
Okay. So I'm going to a little bit past what we said. I'm just going to call that the tension, I'm just call it T, and the string that connects it to the wall. Yeah. Okay. Very good. So I figure that's everything we need in terms of free body diagrams. Again, the knot is unusual. This is 3 tensions in the geometry of string. Maybe I'll add our theta here, something like that. I did put an F sub S here because we are specifically asking ourselves what are the requirements for keeping this stationary, so I'm going to label it F sub S for static friction. Okay, so next step, that's the first step always. Next step is to go on and define coordinate systems and then apply those to Newton's laws applications. I'm not going to ask you for input on this. I'm going to choose standard XY for this guy. Choose standard XY for this guy. And, okay, why not same for this? I happen to have used the same one for all three, but as you now know, I don't need to. Whatever's convenient is fine, so long as I want to tie things together, I treat it as appropriate. All right, so step 2, coordinate system. Step 3, applying Newton's laws. Okay? So just by looking at this, how many applications of Newton's laws do you expect to be applying for this problem? And I know that's a slightly open question, but what I really want to know is how many equations am I about to write down. So by looking at this, what I'm asking is, in how many free body diagrams and in how many perpendicular directions is there something going on that I need to worry about? Put it kind of vaguely. Yeah. So that's certainly true, 2 directions, X and Y, for some of these objects. But if I was to ask you to tally it up for all of them, and just give me a sense of how many equations in total you expect to be writing down in a couple of seconds, what would you say?
2.
Let me push you a little bit more. So I want to write down Newton's law expressions for presumably all of these free body diagrams, these free bodies. So in this case, clearly there's something going on in what I've defined as both X and Y. So I'm probably going to apply Newton's law twice for this diagram. And if I was to go through that line of reasoning for the other 2 and add them up, so how many times do you expect I might write Newton's law equations on this one? Just give a wild, crazy answer. Yeah.
2.
Right. So I'm probably doing 2 Newton's law equations for this. What about this one? 1. Right. So by looking at this, you're getting into this point now where it's becoming habit. I'm expecting to write 2 equations for this because there's things going on in more than one direction. Same thing here. Here I've only got things acting vertically. So I can only write 1 non-trivial Newton's law application. So I'm expecting to write 5 equations in total. All right, so let's jump in. Let's start off with object B. So I'm looking at B in the X direction, then B in the Y direction, then I'm going to look at A in the Y direction, then I'm going to look at the knot in the X direction, and then I'm going to look at the knot in the Y direction. So help me out here in terms of Newton's law expressions. What does a Newton's law expression for B in the horizontal direction look like? Let's get some new victims. Yes.
You know that for the X component of B, the summation of the forces should be 0. So you can just do then that means that TB equals FS.
Okay. So I'm going to write it in a slightly different way, but follow this in a very kind of formulaic way. I'm going to choose plus x to the right, so plus 2b minus fs equals, and yes, this is in some sense a non-action application of Newton's law. So normally I would write here mb times the acceleration of b. Okay, I'm going to leave it like that just for a moment. What about in the y direction? Newton's law expression in the y direction. Again, following this very sort of mechanical. Yeah.
Oh, so you can say MB minus is MB.
Okay. Okay. So I guess that would be in the x direction. This would be in the y direction. But what do we know? Okay, so we certainly know in the y direction there's no motion, there's no acceleration, so this is 0. And in the scenario we're talking about here, where we're looking at this maximum scenario where it's still not moving, again, I know this is 0. Okay.